Today we're going to be going over a different way of expressing a logarithm with a base and an argument. It's called a change of base formula. It's helpful for you if you're in press to test mode for your calculator. And we're also going to be solving exponential equations with different bases. They can't be simplified to the same base. So what I want you to do is I want you to do 1, 2, 3, and 4. Pause the video, take 6 minutes, and do 1, 2, 3, and 4. So, number 1, I have an exponential equation. I can look at the base on the left side of the equation is 3, the base on the right side of the equation is 27. Remember, we need to have the same base here. They do not have the same base, but we can rewrite 27 so it has a base of 3, which is what I'm going to do right now. So this would be 3 stays to the 2x minus 1. And then 27 I can write as 3 to the third 4x minus 7. And now I can continue to simplify this. Looking at the right side, power to a power, I multiply. So the left side stays the same. And the right side would now be 3 to the 12x minus 21. So we now have the same base. We can just set their exponents equal to each other now, since we have the same base. So this would now be 2x minus 1 equals 12x minus 21. And continue to solve for x there. So I'm going to get all my x's on one side. I'm going to get the constants on the other. So it would be 20 equals 10x. Divide by 10 on both sides. You're going to get x equal to 2. And number 2, the left and the right both have different bases, 125 and 25. We want to see if we can get them to be the same base. How can I get 125 and 25 at the same base? Think 5. So 125 would be 5 to the third to the 8x plus 9. And 25 would be 5 squared to 7x plus 16. We have a power to a power. So now we will multiply the exponents. So that would be 5 to the 24x plus 27 equals 5 to the 14x plus 32. Now I'm just going to want to solve for x. We have the exponents are the same. Bases are the same. So now we can set the exponents to each other because we know the exponents have to be the same if they're equal to each other. So that would be 24x plus 27 equals 14x plus 32. Get the x's on one side. I'm going to choose the left side, so I'm going to subtract 14x on both sides. So that would be 10x. I'm going to subtract 27 on both sides equals 5. You should get x equal to 0.5 or 1 over 2. And number 4. So number 3 and 4, they only have exponents on one side of the equation. So the way I'm going to try and solve this for number 3, what we're going to try and do is get that x by itself. What's the inverse operation to raising to the x power? Well, it's going to be logs, so we're going to log both. We're going to log the base is going to be the same base that is on the exponential, so it'll be log base 3. It always equals the exponent. And our argument is 7. That's all we got to do for this one. And for 4, very similar thing. Our variables in the exponent. So we're going to want to use logs, so it'll be log base 4, and it equals the exponent, because it's the inverse operation to an exponential, and my argument goes there. X is not solved for yet, we just have to do one more step and add 20 on both sides. So log base 4 of 18 plus 20 equals X. So that's 1 through 4. We're going to be going on, we're going to be learning the change of base formula and solving exponentials that do not have the same base. So we could rewrite 1 and 2 with the same base, but we're going to solve them without being able to write them with the same base. So what should I know by the end of the day? I can use the change of base formula to evaluate any logarithm. I can mathematically show how to obtain the change of base formula for any logarithm, and I can solve exponential equations without getting common bases. So I want you guys to go to the next page. The top equation I want to do, and then I'm going to have you guys do the bottom equation. So the top equation, still an exponential equation. It just has a couple more steps, so I just want to show you guys one like this. So if I want to solve for x, which is an exponent for us right now, I have to get it by itself. So the first thing I should do the thing that's farthest away from the x, but on the same side. So I would deal with the plus 2 first. I'm going to subtract 2 on both sides first. Subtract 2, subtract 2. We're going to get 20 times 4 to 0.1x equals 16. Now it's important to note here that exponent, the 0.1x, is only on the 4, not on the 20. So that means our next step is we're going to have to divide by 20 on both sides of the equation. And that's going to leave us with 4 to 0.1x equals 16 over 20. You can keep it at 16 over 20 if you want to. You could simplify it. I'm going to write it as 0.8. So now we have a more simplified exponential equation. I'm going to convert this into a logarithm. And why would I do that? Well, I'm trying to get x by itself, and x is an exponent. So logs are the inverse operation to raising something to a power. So that would be log. My base is the same as the base in the exponential, base 4. That's going to equal my exponent, which is 0.1x. And my argument, 0.8. And my last step to get x alone, I'm going to divide by 0.1 on both sides. And now my x is going to be all by itself. So my answer is going to be x equals log base 4 of 0.8 over 0.1. And we don't want a decimal in the denominator, so I'm just going to make it look a little nicer. The same thing as dividing by 0.1. It's multiplying by 10. So that would really be x equals 10 log base 4 of 0.8 would be my answer. I want you guys to try that second one by yourself. So pause the video, take 3 to 4 minutes, and try that second one. So it's very similar to the other one. We're going to take all the same steps. So I have to get x by itself. So I'm going to add 11 on both sides. You would have 35e to the 8x equals 36. Have to still get x alone. That 8x is only on the e, not on the 35. So I divide by 35 on both sides. That cancels. We'll be up to the e to the 8x equals 36 over 35. So I'm going to take this out of exponential form since my variable is an exponent. So that would be log base e, which I can write as ln of 36 over 35 equals my exponent, which is 8x. And to solve for x, I just divide by 8 on both sides. So x is going to equal ln of 36 over 35 divided by 8. And it says round your answer to the nearest thousandth. So we're going to want to put this in the calculator at the end. So in your calculator, I would put it exactly how you see this. So a way to get to a fraction is you press alpha y equals. This just limits the mistakes you could potentially make. So ln, and I'm doing alpha y equals again because I wrote that other, the 36 over 35, it's a fraction, 36 over 35. And the parentheses there. On the bottom, the denominator is 8. Press enter. And we want to round to nearest thousandth. So that would be x equals 0.00 nearest thousandth. You round that up because it's a 5 after the 3. 4. And that would be our answer. So let's go to the next page. What I want you guys to do here is I want you to solve this equation, 14 to the x equals 29. And don't do it how we have been doing. You can, if you split it up, you can solve it the way we've been solving it on the right side. But on the left side, I want you to try to solve it by using the hint. So the hint says try to do the inverse operation of an exponential on both sides of the equation. And then you're going to maybe hopefully see what you can do after that in order to get x by itself. So I want you guys to take 3 to 4 minutes, try and do that. Pause the video and play it once you're done. So the inverse operation to an exponential. What is that again? That's logging, so we're going to want to log both sides of the equation. And this is important to see why we're going to do this. So let's first log both sides. So we log 14 to the x equals log of 29. So I'm going to log both sides of the equation. Now, what could we do next that would help us get the x by itself? Or what's the only thing we could really do here? Think back to the properties of logs. Whenever I had a log with an argument that was raised to a power, so in this case, our argument's raised to the x, 14 to the x, I could bring that x out in front. So now this would be, I could rewrite this as x log of 14 equals log of 29. And now what I can do to get the x by itself, I can just divide by log 14 on both sides. And now the logs 14 cancel on the left side, and now I'm going to be left with x equals log of 29 over log of 14. And that's going to be my answer. And I think it's important, this is the most important part. Why would we want to do the inverse operation of an exponential on both sides? So why would I want to log both sides of the equation? Think about that for a second. What does it allow us to do? It allows us to get that exponent, which is x. Once you write like that, our exponent now, our x, can now get, because of the properties of logarithms, can now be written as a coefficient. And now since it's a coefficient, we can divide by what it's multiplying on both sides to get that exponent by itself. So I also want to show you guys the equivalent way of doing this. And that way, the way we just did is really going to help us out down the road. You're going to see that in a couple minutes. But you also could have done my log take it out of exponential and put it into logarithm form. So log has a base of 14. It's going to equal the exponent, which is x, and the argument goes here, which is 29. So if you notice, log base 14 of 29 is equal to x, and so is log of 29 over log of 14. This is what we call the change of base formula. You can rewrite log base 14 of 29 as log of 29 over log of 14. And I want to show you that I want to show you guys by putting that in the calculator that is indeed true. To show in the calculator, I first do log base 14 of 29. So I press math. I go to log base 14 of 29. Press enter to see what it equals. And now I'm going to do log of 29 divided by log of 14. We should get the same exact thing, and we do. So it's just a different way of writing the logarithm with log base of an argument. And this is going to be really helpful. Let's go back to the calculator real quick. If your calculator is in press to test mode, I know some tests do require you to be in press to test mode. So if it is in press to test mode, you cannot do the math log base and get the specific base on it, but you could always use the log button. So you could use a change of base formula. So that's why this is important to know. And also down the road for solving equations, this is going to be much easier. So that's the change of base formula. So I just want to show you guys a way I remember the change of base formula. Is an easy way to remember it is it's always the log of the number that's on the top of if you look at the number on the top, which is the argument, so it'll be log of 29 in this case, the argument, over the log of the base, or which is on the looks to be on the bottom of the log, so it'll be over log of 14. That's how I always remember the change of base formula. So just a little official blurb about the change of base formula. So for any log base b of x, that is going to be equal to log of, you can really have any base on this, but let me read it first. So it'd be log base a of x over log base a of b. Notice the argument goes on the top of the log, the base goes on the bottom of the log. And what this means is the a right here, the a's, it just means you could really have any base on the logarithm. But since I think the easiest one to use is the common log, which is just log, because your calculator has an easy button for that, I just always convert the change of base formula into log of x, log of the argument, over log of b. You could also do, if you want to, since we can use any of them, we could really do ln of x over ln of b also. Let me show you guys that. So I could also make this, instead of logging both sides, I can do ln of 29 over ln of 14. And you might think that's not going to equal the same thing, but it is, because it's the logs both have common bases. So let's go back to the calculator and let's do ln, alpha y equals ln of 29 over ln of 14, and you'll see we'll get the same exact thing. So you could really do any log as long as it has the same base for the change of base formula. I just want you guys to use that and do 1, 2, 3, 4, 5, and 6. I want you to solve 1, 2, and 3 like we did up here using the change of base formula. So pause the video if you haven't, take 3 to 5 minutes and do that. I'll show you the answers and when you play the video. Here are the correct answers. As you see on the left, I did the way by using the showing the change of base formula. On the right of each in the red, I did the way of just converting out of exponential into logarithm form. And both are great ways. You'll just see the way on the left is how we're going to do it when we get more advanced equations than just a base to a power equals a number. So they're equivalent answers, so they're the same exact thing. Either answer is great and works. And check out 4, 5, and 6. And notice for 3, the one thing I want you guys to notice for 3 is, if you notice ln of e, I didn't even bother bringing the x out in front of me. It could have, because ln and e just cancels out. They're inverse operations of each other. So we're just left with the x. So that's why it's just x equals ln of 1024. Let's go to the next page. The equation at the top, 3 to the 2x plus 9 equals 4 to the 3x minus 1. It's an exponential equation. How do I know that? The variables are in the exponents. So this is an exponential equation. I can't rewrite 3 and 4 are bases to have the same base. So in this case, we can't just set the exponents equal to each other once we get the same base, because we can't get the same base. It's 3 and 4. This is where we're going to have to do something different, which is why we just went over the change of base formula. So think about what we did with the change of base formula in order to get the exponent, get the variable, not the exponent anymore. So we logged both sides. So when you log both sides, let's first do that first. So it'll be log of 3 2x plus 9 equals log of 4 3x minus 1. So first of all, we can log both sides because logging is just an operation. It's like subtracting 5 on both sides or multiplying 2 on both sides. That's going to keep an equivalent equation. So both sides are still going to remain equivalent if we do the same operation to both sides, which in this case is logging both sides. But why do we choose to log both sides? What does that allow us to do? It allows us to take the exponent, which is 2x plus 9 here, and 3x minus 1, and write it as the coefficient in front of the logs. So now I can rewrite this as 2x plus 9 times log of 3 equals 3x minus 1 times log of 4. So no longer is our variable an exponent. It's now a coefficient, so it makes it easier to work with. We can actually solve for x now. We couldn't solve for x if we just kept it as the exponent, because we don't have common bases here. So it's very important to write it exactly like this. I'm going to highlight something. It's very important that we use those parentheses there. So these parentheses and these parentheses. If you don't use those parentheses, then you're not going to distribute 2x plus 9 with log 3. Because that's where you're going to need to do. You need to multiply everything of the exponent by log 3. So what I mean by that is this would now be 2x log 3 plus, and we multiply the 9 and also 9 log 3. If you don't write with the exponents, you're not going to see, sorry, if you don't write it with the parentheses, you're not going to see to do that. So make sure you write with the parentheses. That is might be the most important step of all of this. Because if you don't write with those parentheses, you're going to get the question wrong. So same thing over here, that 3x gets multiplied by log 4, and so is that negative 1. So that would be 3x log 4. And then negative 1 times log 4, just minus log 4. All right, so when we solve any equation, we always want to get the variable alone on one side. We want to isolate the variable. Here our variable is x. So we want to get all the x's on one side of the equation. So what I'm going to do is I'm going to get the x's. It doesn't matter what side you get them on. I'm going to get the x's on the left side of the equation. So in order to do that, I'm going to subtract 3x log 4 on the right side and also subtract it on the left side. Once you do one side, you have to do the other side, just like we solved all the other equations. That's going to get this to cancel over here, so we have no more x's on the right. And now since we have all the x's on the left, I'm going to get all the constants on the right. So I'm going to do similarly. I'm going to subtract the 9 log 3 on the left to get that to cancel out. Subtract the 9 log 3 on the right also, except to do it on both sides of the equation. Now if you look, we have all our x's on the left side, all of our constants on the right. You cannot combine these because they are unlike terms. They do not have the same base. So that would be 2x log 3 minus 3x log 4. We cannot combine those. Equals what's left on the right, minus log 4, negative log 4, minus 9 log 3. So we accomplished our goal of getting all the x's on one side. Now, how are we going to get that x? So we just only have one x on the left hand side of the equation. Well, what we could do is they each share an x, so we could factor out an x and see what it looks like. So now it would be factor out the x. So what we're left with now is 2 times log of 3 minus 3 times log of 4. Once we factor out the x, in the right stays the same. Negative log of 4 minus 9 log of 3. And once we do that, we can now divide by 2 log 3 minus 3 log 4 on the left. And what you do on the left, you also need to do on the right. Now, why would we divide by that? Well, you always want to do the inverse operation of what's happening to our variable that we're trying to get by itself. It's being multiplied by 2 log 3 minus 3 log 4. So you want to do the opposite and divide by 2 log 3 minus 3 log 4 on both sides. That would get all this to cancel on the left, so we're left with just an x on the left, and that would equal what's on the right. So that'd be negative log of 4 minus 9 log 3 all over 2 log 3 minus 3 log 4, and that is our answer. Circle that because that is our answer. And we can also, a question like this might ask you to round it, so I want to show you guys how to put that in the calculator. I would put it exactly how you wrote it. So in your calculator, if we're looking around this, it's a fraction. So I'd press alpha y equals n over d, stands for numerator over denominator. That'd be negative log of 4. Make sure you close the parentheses there. Minus 9 log of 3. Close the parentheses there also. over 2 log of 3 minus 3 log of 4. And you should see what it would round to. Rounding to the nearest thousandth would be 5.747. So here, I'm going to write x is about 5.747. You could also write that if it asks you to round. So a couple key things I want to make sure we go over one more time. Why do we take the log of both sides? Well, we know we have to log because our variable is an exponent, so we have to do the inverse operation to an exponential, which is logging both sides. You could do this if they had the same base. It's just a little bit more work doing this if they had the same base, but especially if they don't have the same base, we can't simplify our exponents to the same our exponentials to the same base. You have to log both sides. Make sure you write with the parentheses here. That's a very common mistake not to write with the parentheses. That allows us to see that that exponent's getting distributed with the log of the argument. And then every way of thinking is the same after that, as if we're solving an equation. We get our variables on one side, so that's what we did here. We get our variables on one side, and then we have to factor out an x here in order to get just one x on the outside in order to get the x by itself. I want you guys to take your time, do 1 and 2, pause the video, and play it once you finish 1 and 2. So for 1 and 2, what you should notice is that they're very similar processes. So because they're both exponential equations and we can't get the base to be the same, we log both sides. And what does that allow us to do? That allows us to bring our exponent as the coefficient, as you see here and here. Same thing here and here. That allows us to bring the exponent as a coefficient. Remember your parentheses. If it's more than one term, then you would multiply that coefficient with the log. Make sure you distribute that in there. As you'll see, I'll do it for the number 1. That 3x gets multiplied by log 8, and that 10 also gets multiplied by log 8. And you would want to get your exponents all on one side. So my variables all on one side. So I get my x's all on one side there. My x's are all on one side here. You need to factor out that x so we can get only one x shown on that left side. And then since x is being multiplied by, if you look at number 1, in this case, log 5 minus 3 log of 8, you would divide both sides by log of 5 minus 3 log 8. And the same thing over here for number 2. Now, a question didn't say round, so I didn't round the answers. And those are the answers to 1 and 2. So the success criteria is after this, and just the classwork. It's only 9 questions. That's it.